if this is an inclined plane, there's no friction, does this look balanced to you? No. Does it? No. When I look at that, for every left there's a right? No, there's not. This looks like it could be balanced, maybe up and down, but it's clearly not balanced. Now, we know what the calculator does, right? This isn't a surprise. We're very aware because we showed it in class. The thing just slides this way. So it's not like it's a mystery what's happening. You're supposed to use that. I had 2 students come in for tutoring this morning. Both asked the same question. I don't know where I'm supposed to put the MA in the problem. And I know that means that there's got to be some of you who feel the same way. But after we do this part, what's your next step in the set of things you're supposed to do? What's that? Right, we need to put a coordinate system here. This isn't arbitrary, and I didn't do this in your class, and I probably should have, because I started realizing I need to do it in every class, I think. First, this is a coordinate system, right? Not this. You see why they're different, right? So when you're doing your work, and I am grading your work, if your coordinate system looks like this, you are not going to get credit, even if it's just you being sloppy. But I've had people on their recent quiz decide that they needed to make one of these line up with one of the arrows and one of them line up with the other arrow. So they quite literally turned in this for their coordinate system, because it has to line up with the arrows. That is not what you are doing here. Right? What you're supposed to be doing is taking something you already know about, an XY plane, and applying it to your problem. Even that takes some discussion, I think, but at least start with the knowledge that you're going to take this and put it or apply it over the top of your system. Now, how you do so, that part is up to you. You could put it anywhere here you like. What you're trying to do is find a way to make it easier for you. But you could decide, okay, this is my coordinate system. I have decided this is the direction of X and Y, and you could work the problem from here. You've just made it really hard on yourself. So I gave you 2 things to think about in trying to decide, how do I line it up? And I'm getting the impression you guys just don't like having freedom to make a choice. You want me to tell you how to do it. And what I'm trying to say to you is that it depends on your problem. You have to make a choice dependent on the problem. It's like choosing whether one direction is positive or the other direction is positive. You make a choice that fits for you and will help you solve the problem best. So what I said to you is, look, try and line it up with the forces if you can. Now, you can't line this one up with both forces at once, can you? There's no way to do so. So I'm still going to have one of them that's not lined up correctly. But if the problem is accelerating, if you really want this to be the easiest way for you to solve it, then you need to line it up with the acceleration. What you're doing when you say that, when you're lining it up with the acceleration, you are forcing one of your directions to get MA and one of your directions to get 0. That's what you're doing. If I leave it like this, then we know the object actually accelerates. Let me see, let me draw that. Let me just take the arrow. We know the object accelerates this way, right? So the acceleration is going to be both in the X direction and the Y direction. So both of them would have to get MA. That's an impossible problem. It's hard for me to solve that. So knowing that there's a way to make one of them 0 is always the best way to go. So in doing this, take this, try and line it up in such a way that it is aligned with the acceleration. And if you do so, you can go net force in one of my directions is MA, and net force in one of the other directions is 0. It depends on which one of these you label X and which one you label Y. Is that all good? You following that now a little bit? So I generally say it's also best to make the direction of the acceleration positive. This problem is not complicated, but some future ones will be, especially when we start having multiple things moving at once. Making a positive common direction, it becomes harder. So I'm making this X and this one Y. Now, some people I've noticed like taking this and turning it so that the X and Y are still horizontal and vertical. It's fine. Doesn't matter what you do with this next. It doesn't bother me to have it at an angle, but I mean, you can just take your piece of paper and turn your paper to make it, in front of you, X and Y. Because the next thing you have to do is draw a triangle to break up your one off-axis force into components. But you need to realize, too, that you have to put the 20 degrees somewhere. And some people don't know whether the 20 goes in A or B. Where does the 20 go? B. I gave you a rule, a cheat. And that cheat is that it goes between the weight and the line through the normal force. So that's got to be B. So here's the weight. That's the normal force. This has to be 20 degrees. Now, the reason it might be better for you to draw yours like this or turn your paper is because you do have to draw a triangle here. And so many people do this just fine, but there's this handful of people who screw this up. The weight is going to be the hypotenuse of this triangle. And when it's drawn like this, it's easy to see that one of my arrows will be like this, and one of my arrows will be like that. Right? The right angle has to go between the two components. But I promise when we do this in a day or so, one of you, when it's like this, is going to draw that triangle wrong. And you're going to take and make the triangle look silly. So I'm showing you what silly looks like because I don't know why people do this. But they'll draw the right triangle like this. And when you do, it's going up on the board. We're going to all have a good look at it. So don't do this. Do you see why this is wrong? I mean, you've made the wrong thing the hypotenuse. And your components aren't at a right angle to each other. More importantly, your components are supposed to line up with X and Y. And although one of them does that line up with the X and Y? So make sure you draw your components correctly. You could, and I hate saying this, and even recording it, you could memorize it. This is going to be W cosine 20. And this one's going to be W sine 20, or whatever your angle is. It'll always be true that the one that's aligned with the X direction is sine, and the one that's aligned with the Y direction is cosine. It's almost always going to be true. You could memorize that. Every inclined plane is going to be the same kind of problem, where the weight's going to get broken up. So unless you change or don't do your coordinate system like this, that's going to be true. Once I've done that, remember the idea of components is they redefine my original vector. So I can get rid of the original vector and these two vectors take the place of the one vector. And now I can apply my rules. I go back to doing a Newton's law problem because this wasn't the Newton's law part. This was just figuring out vectors. But Newton's law actually is just applying these two rules. So we get W sine 20 equals MA, and normal minus W cosine 20 equals 0. All good so far? All right. This is where you have to start doing analysis. We got to start thinking for yourself a little bit. But there's probably going to be some substitutions that are going to start showing up here. For example, is there a substitution you're aware of that we could use to try and reduce this? Yep.
Wait until math and graph.
Yep. we can substitute mg in for weight. That's a very likely thing you will have to do. In fact, you'll be doing it so much, you'll probably stop writing W and just write mg most of the time. It's not the only substitution we're going to have, but it's one of them. Now, do you see that you could figure out the acceleration without knowing the mass? Oftentimes, the mass on these kinds of problems will cancel out. Not always, but often they will. And so here, the answer is just going to be g sine 20. So I didn't give you the mass of the calculator, but you didn't need it for an answer that was just find the acceleration. G is 10, sine of 20 is 0.34. We find the acceleration is 3.4 meters per second squared. Questions? Again, it's always easy when Mr. Shelton does these problems. All right. I want to try something new today, okay? I want to add something to our problems. And I want to talk about friction. Friction is a force, so it's in newtons, the same way that the normal force is a force, and it is in newtons. This particular arrangement is the arrangement we talked about when it comes to static friction, in that it is a reactive force that will increase until you reach some maximum. And it's related to the normal force. But we use a symbol for this, not a percent sign. We use a symbol. And the symbol that is used for friction is lowercase mu. So, since I think this is probably the first time you guys have used lowercase mu, let's talk about what lowercase mu looks like. So, there. If I have a P and a U and a K, mu is like a U with a little bit of flair. Does that make sense? That's how it's written. The little hangy-downy part hangs down below the staff like a P would, but the size of the letter should be to the middle. When it's typed, often that the hangy-downy part is straight. So don't be confused with the symbol. Generally, static friction and kinetic friction will have different values of mu. So if you have two surfaces, rubber on asphalt, there will be a static friction mu and a kinetic friction mu for the same surfaces. We call this the coefficient of friction. That's the language that's used here, the coefficient of friction. I put an S next to it when I'm dealing with static friction. Now, if you don't like saying coefficient of friction, then use the word percentage in your head. Coefficient just means number in front of. That's all it means. So the coefficient of friction, it's unitless, it's the number in front of. It's still just a percentage. The frictional force will be a percentage of the normal force. This is always a number between 0 and 1. It is possible to get coefficients greater than 1, but you're talking about glue and stuff like that, right? Things that would bond two things together. Generally, it's going to be a number between 0 and 1. If you work something out in a lab and you get a number that's greater than 1, you've probably made a mistake. Now, full disclosure, and to make sure I've covered everything, this is how we would write the equation for static friction. For kinetic friction, I'd put a K next to the friction. It is not an inequality, it's an equal sign. Kinetic friction is a constant. Once you have broken static friction and you're sliding, your kinetic friction will be constant. It's just going to be mu with a little K next to it times the normal force. It too is called the coefficient of friction. So there's the coefficient of static friction and the coefficient of kinetic friction. For the most part, static friction is greater than kinetic friction. For the most part, static friction is greater than kinetic friction. Imagine if you have two surfaces that aren't sliding, there's time for the molecules to kind of connect up. Once you break that, they never really connect up as well, so that's why static friction tends to be greater than kinetic friction. Because once it's moving, it's harder for the molecules to kind of connect up. Those van der Waals forces between molecules and surfaces, they don't get to be established, so the friction goes down. So if you break static friction, what you get is a resulting kinetic friction that is usually less. Most of you kind of already know this. If you've ever had to push something across the floor, it took like more force to get it started, but then once it was already moving, you didn't have to keep pushing as hard, you could push less. That's because the amount of friction that was required, the amount of force that was required to overcome friction went down after you started it. So that's pretty typical to have this number be greater than this number. But remember, this is an inequality. I keep bringing that up because you don't necessarily know when you're at the maximum here. That's why we have to make sure you know it's an inequality. You have to use the inequality sign.